Hello everyone! Today we are going to talk about PWM and what you can do with it. PWM stands for Pulse Width Modulation, and it consists of producing a square wave which you can control the up or high time. In a PWM signal, the minimum and maximum voltage are the values that limit the wave's oscillation. The space between them is called amplitude. A cycle is the interval of the wave where you can find one full repetition. The time a cycle takes to finish is called period, and the frequency is 1 over period, which gives you how many cycles are in a time unit, usually a second. A very important concept in PWM is the duty cycle. The duty cycle represents how much of the period in which the signal is high. In our wave, the signal here is high, and here is low. To calculate the duty cycle, you need to know how much of the period the signal is high. Let us set our high time as 6 milliseconds, our downtime as 4 milliseconds, and our period as 10. Now, let's use a simple rule to calculate the percentage of the period in which the signal is high. 6 relates to 10 the same way as our variable in percentage relates to 100%. If you solve this, you'll see that you get 60%, meaning that the signal is high 60% of the time. Let's imagine a PWM signal that oscillates between 0 and 5 volts. Let's say this signal has a duty cycle of 50%. Something interesting will happen to the output voltage. Instead of being 5 volts as expected, it will now be 2.5 volts. Simply putting it, this is because in a PWM signal you multiply the max voltage by the duty cycle. This is the formula. By applying this to our situation, you will see we will reach a 2.5 volts. Let's see what happens to the different components of the wave when I increase the duty cycle. As you can see, when I increase the duty cycle, the output voltage also increases. And when I decrease the duty cycle, the output voltage also decreases. Keep in mind that the output voltage can only oscillate between the minimum and the maximum of the PWM signal. Let me show you this example in real life. We are going to use an Arduino, a breadboard, a LED, and any resistor between 1K and 300 ohm. If you look closely at an Arduino, you'll see some pins have a tilde symbol. This means these ports can output a PWM signal. Now let us set up a simple LED configuration. Connect the Arduino power to the breadboard. Next, place the LED on the breadboard and also the resistor between the LED and the ground. Now, simply connect a cable between any port that can handle a PWM signal. Last but not least, we have to create a program to control the PWM port. Assign the port that you connect to your LED into a variable, so we'll call it PWM. Now, this byte variable will represent the PWM value. The reason I chose a byte variable is because the PWM, the Arduino, has a resolution of 8 bits. So you have 8 bits or a byte to encode the value of your duty cycle. 0 means 0% and 225 means 100%. In order to control the PWM ports in an Arduino, you use the analog write function. The first parameter is the number of the pin which you want to control, and the second is the value of the duty cycle ranging from 0 to 225. We want the PWM value to slowly increase with time. For that, we will increment the variable each time the program goes through the loop. In order for this process to be slow, we will have to introduce a little delay. 20 milliseconds should do. Now, we don't have to reset the byte value, because when it reaches its maximum, or 225, it becomes 0 again. At your left, you are looking at my old oscilloscope showing the PWM signal. At your right, the LED becomes brighter the higher the duty cycle, and it becomes less bright the lower the duty cycle. Thank you for watching, and I will see you in the next video.
Hello, my name is Carlos Osorio. I am an application engineer at Marvellous, and in this video I'm going to show you how to design a speed controller for a DC motor using a PWM drive. What you're seeing on your screen is a Simulink model. We have a model of a DC motor here connected to an H-bridge amplifier connected to a 12 volt DC power supply. This is an open loop configuration and the amplifier is in average voltage mode. I am feeding in a duty cycle that is going straight to the amplifier. If I run the simulation, what we can observe here is the speed of the motor changing, ramping up until it reaches some steady state, and at time equal 1 second it goes down, because at time equal 1 second what I am doing is I am applying a step change in the torque load. You can see the current variation here, and you can see a constant voltage being applied. Again, it's an open loop configuration, so the voltage is not changing. And right now we're operating at 80% of 12 volts, which is 9.6 volts. So the first thing I am gonna do is I am gonna close the loop to design a controller. So my reference now is gonna be reference speed. We're gonna pick 600 radians per second in this case, which is well within the range of operation of my motor. And I am going to open my Simulink library browser, go to the discrete blocks and bring in a PID controller block. Let me just flip it so I can connect it. So this block, when I open the tab, automatically lets me select the structure of my controller. So if I want a PI or a PD controller, we're going to pick a PI in this case. I am going to set up the sampling rate for this controller to be 400 Hertz, which is the frequency of the PWM that we're going to use. And the one additional change I am going to do is I'm going to limit the output to be between 1 and -1, because the output of the controller is going to be the duty cycle for my amplifier. Let me make it a little bigger here. And of course, it's not a PID controller anymore, it's a PI controller. So when I run the simulation again, the performance of my controller is not very good because I haven't tuned my controller at all. The response is very choppy, and actually if you look at the voltage is fluctuating between +12 and -12. So that means the output of the controller is fluctuating between 1 and -1. So the next step is tuning this compensator. So I'm going to use the tune function on this PID block, which is going to linearize the plant. I'm going to skip the default linearization, which is occurring at time equals 0, and I'm going to pick a good operating condition. I'm going to pick a simulation snapshot, in this case of 1.5 seconds, which is where I am applying my extra load, and I'm going to ask the tool to re-linearize the system. It's going to run the simulation up to 1.5 seconds. It's going to pick the states at that point, and it's going to do the linearization for me. It not only has done the linearization for me, but it has also designed a compensator for a smooth response, 60 degrees phase margin. So it has optimized the relationship between the P and the I. But this is an interactive tuner, so you have control over the design. If I want my controller to be slower or faster, I can use these dials to adjust the performance of my controller. And of course, this will be based on whatever requirements you might have. So let's say we have a requirement where the bandwidth of our controller needs to be 10 Hertz. 10 Hertz is 62.8 radians per second. And maybe I have a requirement for the maximum overshoot that I can accept. In this case, right now, we have 12.6% overshoot. That might be too much. So I'm going to play a little bit with my phase margin. Maybe let me increase it a little bit, which is going to bring down the overshoot. There, I am below 5% now. So the point I'm trying to make is that you have the ability to interactively tune the compensator until you're happy with the performance. Once you're happy with the performance, you just hit apply. Down, and that would automatically update the parameters in the block. And so when I run the simulation now, what you're going to see is the implementation of the controller that I just designed. I am testing my controller against a full nonlinear simulation here. Notice that there's a saturation element here, and that's why you see this little peak at the beginning. You can see the voltage saturating at 12 at the beginning, and I'm asking it to ramp up to 600. There's a little blip down, but it recovers very quickly and comes back. So I'm pretty happy with the performance of my controller right now. So then the final step will be, let me implement this in a more realistic way, which is introducing the PWM driver and the switching dynamics. So this block here that I have, where I have my H bridge, which is in average voltage mode, I can directly from the menu here, there's a drop-down menu here that allows me to switch the technology here. I can implement a MOSFET bridge. I'm going to select an IGBT bridge in this case. This is a block from our SimPower Systems library, and now instead of being an average voltage model, this block is implementing 4 IGBT devices for the full H bridge. Now these devices have to be driven by pulses, not by an average duty cycle. So what I'm going to do is back to my Simulink library. Under the Simscape heading, you'll find SimPower Systems, and in SimPower Systems, in the Extras library, under Discrete Control Blocks, you'll find a variety of very useful controls blocks. One in particular, which is the Discrete PWM generator. I'm going to bring that into my model here. So this block can be set to be a 2-arm bridge or a 3-arm bridge. In this case, we have a simple 2-arm bridge. We're going to pick the carrier frequency to be 400 Hertz, as I said, and the sample rate for this block is going to be the sample rate of my model, which is TS, which is in this case 2.5 e to the minus 5, which is 100 times 400 Hertz. So now let me run the simulation again. And what you are observing now is the full behavior of the system with all the switching dynamics included in it. You can clearly see the effect of the switching dynamics on the current. You see it a little bit on the speed, but the performance is pretty good. The voltage, actually, if I zoom in a little bit, you will see the voltage is changing based on the duty cycle, and you can see the dynamic effect in the current here. This is the inductor in the motor charging and discharging at that PWM frequency. On this side, I have actually the pulses. If you want to look at the pulses, I am monitoring that, so you can see how we're sending 4 pulses directly out of this discrete PWM generator. 2 pairs of opposing pulses that go to each one of the arms of the inverter.